So I begin by thanking ICTS for organizing this meeting every year. So in the last few years, I've been working on various self-assembling problems and self-organization problems in soft matter systems. And today I'll be talking about spontaneous helix formation in a semi-flexible polymer, a polymer which needs energy to bend. And I want this helix to form by using generic potentials, by which I mean that I don't want to use torsional potentials, because if you have chemistry dependent torsional potentials, yes, it can form a helix, and I want to do it without packing effect, so basically in a freestanding polymer. Since this is a short talk, I shall begin with the acknowledgements. So the work was done by Debarshi Mitra, who is my PhD student, and he is putting up a poster. So if you find my work to be of interest, you can visit his poster to get to know the details. I thank K. Guruswamy of NCL for discussions, and funding has been by DBT, ICER, and DST. Okay, so what is the broad question? The broad question is whether a helical conformation self-emerge in an elastic filament or in a semi-flexible polymer, where I don't want to use torsional potentials or hydrogen bond mimicking potentials as you have in helical DNA, where hydrogen bonds get the helix. And why do I want to look at it? Well, if I can figure out how to get self-emerging helices and freestanding polymers at the micron to nanometer length scale, then one can make helices for use in microrheology, as Ambarish Ghosh does in Bangalore, or for springs in NEMS or MEMS systems, or maybe understand the spontaneous helix formation or helical order formation in various semi-flexible biopolymers. So those are the applications. But how did I get into looking at self-emerging helices? Well, it was courtesy K. Guruswamy, who works in NCL, and his student Bipul Bushash, so who basically took a colloid, 1 micron sized colloid, and on top of it, on the surface of it, he had polynipam. Now he took various colloidal particles, put them in a chain, straight line chain, approximately using an electric field, and cross-link them. So what you have is basically a semi-flexible polymer made of colloids, which you can see on the microscope, right? So you can see semi-flexible polymer dynamics under a microscope, because they are made up of colloids which are 1 micron sized. Now this polynipam, whatever is the surface coating, basically becomes to be in a bad solvent in water if you raise the temperature to be above 37 degrees centigrade. And if this polynipam, if this polymer, effective polymer, basically is in a bad solvent, it would like to collapse and form structures like this, which look helical. The question was, can we understand it? How this helical, this emergent helical pattern, if it is a helix, emerges. So this work is still in progress, but this led me to the question that in general, what are the conditions in which helix can, helical configurations, conformations can self-emerge, where I don't want to use chemistry, chemical torsional potentials which depend upon the detailed chemistry of the problem. I want to use generic simple potentials. So that was the broad question. Now, helices have been observed in previous studies. Debashish Chaudhary, who is in the audience, has seen helical conformations where he used a basic central backbone polymer surrounded by branches which are basically polymer rings, and when you confine such an architecture, such a polymer, he was modeling DNA inside a cylindrical cell wall, which was the cell. Basically, he's confining such an architecture, a polymer filament with side chains, ring polymers in the walls, and he gets helical conformations, as he said in the morning. Other than that, Bhanu Nandan from IIT Delhi has put in nanoparticles inside confinement, inside cylinders, and when the radius of these particles and the radius of the confining cylinder hits a certain value, he gets helical organization of these packed nanoparticles. And way back, Jayant Banawar and Maritan have a whole PRE, RMP, a Nature article on packing elastic filaments into helices. But in all of this, there was packing effect involved, which got you helices. I want to see helices where is no packing effect. Can one form? Yes, I figure out a way. So here what I show is basically starting from an initial straight linear conformation of a semi-flexible polymer. There basically thermal fluctuations make it wiggly. And if you put a strongly repulsive Coulomb potential or any other long range repulsive potential, it can get into a helical conformation. But these helices are not stable. They are not like this, they slowly unwind. They are pretty long lived, but they slowly unwind. Okay, so I'll just show you a movie because seeing is believing. So it was like this initially, and you can see helices slowly emerging, which was very similar. I've just made the beads much larger, and you can see that there is some amount of circular patterns which is reminiscent of that of a helix, and that was with strongly repulsive Coulomb interaction. And you get similar structures even if you use a repulsive 1 by r cube potential, long ranged again. So it very quickly starts forming helical conformations here. Okay, so seeing is believing, but eyes can deceive. So the best thing is to calculate order parameters. But before I talk about order parameters, let me tell you about the model. All that I'm using is a bead spring model where I have harmonic spring interaction. The length of the bond is the unit of length in our simulation. I have a bending energy, epsilon b cos theta, where theta is basically the angle between adjacent bond vectors. I use long range Coulomb interaction, repulsive, so I control the value of epsilon c by r, or I can use epsilon d by r cube. Long range interaction is important. What is important, I must stress that I'm not using counter ions. I'm not using evolved summation. I am using 1 by r potential. Okay, so my Coulomb interaction is not screened, and I use a very large box size so that there is no interaction with periodic images, right? And I do a Brownian dynamic simulations, and after that, to ensure that I truly get a helix, I calculate order parameters to identify helices, and there are two order parameters, H4 and H2, and I plot it as a function of time. And let me tell you what this H4 and H2 are. Now suppose you have a polymer which is, you have a helix already, you know, and if you move along the contour, suppose you take two adjacent tangent vectors, Ri and Ri plus 1. Take the cross product. If this was a perfect circle, it would basically point normal of the plane of the circle. But if it's an helix, it will be an angle, I mean, it will be parallel along the axis of the helix. So that is ui, and small ui is just the unit vector of that. Now, if along the chain, you just sum up ui along the chain, and if it is a non-zero value or high value, then you say that, okay, you have got a helix. But if half of the helix goes clockwise and the other half goes counterclockwise, then you would get the order parameter to be 0. So H4 is not good enough, it is good, but you also need to calculate something called the local helical order parameter H2, which is essentially the local dot product of adjacent UIs along the chain. So a combination of these two shows whether you have got an helix or not. And what I show is H1, H2, H3 are three cases where you have that Coulomb interaction 3 independent runs, and in each case you get some helical order parameter as a function of time. It develops rather quickly after time, and I compare it with R1, R2, R3 with 3 different colors where you just have a semi-flexible chain. So if you have a semi-flexible chain, it could also bend and could end up showing some sort of helicity, and I wanted to clearly distinguish when you have a real helix where you have a high value of H2 and H4 compared to what you get when you have semi-flexible polymers wiggling around. So when you have the extra potential you see, I mean the Coulomb repulsion, you do get a helix. Question: why and how are helices formed by a spherically symmetric interaction in a semi-flexible polymer? I wouldn't have expected it. Before I fully explain it, some hints or some observations. At kBt equal to 0, when temperature is not there, there's no fluctuations, and you have a spherically symmetric potential and a semi-flexible energy, you don't get a formation of helices when you have a straight line initial condition. But at kBt equal to 0, if your filament of your semi-flexible chain is slightly bent, uniformly bent, or if it is basically straight, say along the y direction, but there are positional fluctuations in the other 2 directions, which when kBt is finite is given by thermal fluctuations, then you see helix formation. Okay. So temperature does play a role in slightly disturbing it from this straight line initial condition, and the reason helices form can be understood schematically very simply. Suppose this is an initial polymer chain. After a small time, there will be thermal fluctuations which will make the monomers move around, basically give some positional fluctuations along the straight chain. But you have also Coulomb interaction, and that basically puts the particles apart along the direction of the bonds, and that develops to sharp kinks, and the bend energy due to sharp angles is released to form a structure. Basically it's reducing its bend energy with sharp kinks, which results in a helix. This has been basically checked out by plotting the values of different energies, and you can see it in the poster. That was just a schematic explanation. The last point is, okay, helices, you know, they unwind. They're long-lived but unwind. Can one give periodic forcing by switching on and off a Coulomb repulsion, say by change in pH? So basically, and get persistent helices. So what I have done is make the amplitude of the Coulomb repulsion cos square 2 pi t by t, I mean 2 pi t by some time period, and you are basically switching on Coulomb repulsion and decreasing. So what happens is the helices form and then they become straight lines as this amplitude decreases, and form and relax, and so on and so forth. Finally, I want to say that a right balance of spring, bending and repulsive energy is needed to get helices, and that has been in detail analyzed, and it is there in the archive. I have also formed a state diagram which I don't have time to explain, but if you're interested you can look up the poster, and I thank you for your attention.